Hello and welcome back to Mrs. O'Graham's Maths. Today we are going through a practice paper for the Complex Numbers Level 3 external. So this isn't a real paper from the NCEA exams, but it's a parallel one written to be very similar to those ones, and it was one that was used by my school for our practice exams. So for each question, I suggest you pause and have a go at the question first, and then hit play to see the worked solutions. So for this one, we're going to use our calculator. It's a very common type of question that can be done algebraically, but is much easier and faster on the graphics calculator. So we first of all write out what we've been told here, that W and Z multiplied together makes 20 minus 10i. Then what that means is if we have two things multiplied together to make something, then we can divide one by the other to get the thing that we are trying to work out. In this case, we're working out what the D is. So we can turn this into a fairly straightforward division that can be done on the calculator. So we'll type that in, and it's 20 minus 10, and you can either do shift and then I to get the I there, or I'll show you on the next one. We'll do 3 minus 4, and then we go to options, and then right here for complex, we can press that button and we get the I come up here, so you can find it that way as well. There's a few other options under the complex menu that you can do various things with, so it's worth getting familiar with them. So if we press enter, that goes to 4 plus 2i. So that division there is 4 plus 2i. If we equate that to the d plus 2i, that means that d is now the 4. We're just comparing this thing on the left with this thing on the right, so the 4 must be d. For part B, we have these two complex numbers, z1 and z2, and they're given to us in polar form. We want to find the value of multiplying the two things together and draw the position onto the Argand diagram. So if we multiply two complex numbers together, then we will multiply the arguments, so that is, the modulus, 6 times 3, the modulus gets multiplied, and the arguments get added together, so the minus pi by 4 and the pi by 6. Now if you're not great with your fractions, just type them in without the pi on it as a fraction on your calculator and add on the sixths like this. So we're doing that without pi in it, and then when you write it in, you can write down the pi. So 6 times 3 makes 18, minus a quarter plus a sixth is minus a twelfth, so that's minus pi by 12. Now the final thing, to make sure we don't miss anything on this question, draw it onto the diagram. That often gets skipped by students that are just in a hurry to get things done. So we're looking for a length of 18 for the modulus here, and the angle is minus pi by 12, so it'll be somewhere down here in this quadrant, and we're just sketching. It doesn't have to be super accurate. So here we have the value, the position of z1, z2. Now part C is a little tricky to wrap your head around what's happening, so it'll help to have some diagrams with this. So an equilateral triangle inscribed in a circle means that we have a circle with an equilateral triangle inside of it, like that. So that's what we're aiming to think about. Now let's put on the other information. We've got one of the vertices of that triangle is at this particular point. So we know this point here, Z1, is one of the corners of the triangle, and it's on that circle. Now the circle x squared plus y squared equals 4 means that it's centered at 0 because there's nothing here in the x or the y side of things, and the radius is the square root of this number here, so its radius will be 2. That's how I can draw this out. So we've got our first thing set up. Now the radius being 2 gives us a modulus of z1 being 2. The fact that it's at 1 plus root 3i gives us those sides of that triangle there. So the x direction is 1, the y direction is root 3. That means that we can work out our value of theta, the angle just here. So you can either use trigonometry, or you can recognize that this is one of the special angles. It's on the formula sheet with the trig values on there. So theta must either be 60 degrees or pi by 3. Doesn't matter which one you use, whether you want to go radians or degrees. Now, to find the other corners of that equilateral triangle, we know there'll be 3 of them spaced around this circle. So if we split 360 degrees up into 3, then we can count on from there. So if this first one is at 60 degrees, the next one will be 120 around from there. So it'll sit here at 180 degrees. And the next one will be another 120 around from there. So we've got 3 evenly spaced corners of a triangle. So we can set out Z2 over here quite nicely. We're just adding another 120 degrees, or 2 pi by 3. The third one is over on this side, and we can do 120 around the other direction. Since this is 60, this will be 60 underneath here. Or you can add 120 around from that 180 line. Either way is going to work. So now we can write down the complex numbers that they are. So Z2 being over here. Remember, the modulus is still staying at 2. Both of these will still have a modulus of 2. This one's gone around 180 degrees, so it would be written as 2 cis pi or minus pi. Either one's fine. And then this one here, the Z3, is going to be at 60 degrees under that x-axis just here, modulus of 2. So that's 2 cis minus pi by 3. You can do them in polar or rectangular form. So just underneath, I've written them in rectangular form as well. You don't need to show both. Just either one of those would have been acceptable. Part D is a question about loci. So we want to find and sketch the locus of points that satisfy this equation. So a reminder of what this is telling us. So this is modulus means distance. So that's what happens when we get those straight lines. And this is saying that the distance of z to negative I, because it's always a minus the thing, is less than z to 3. So we're looking for the line that goes evenly between negative I and 3. So the perpendicular bisector there. Now to do that, we turn this equation into x's and y's and solve it so that we can get the equation of this line. So we start by stating that z is x plus iy. Then if we rewrite that equation, but with x plus iy instead of z, we get this. Now, modulus means that we are doing the square root of the real part squared plus the imaginary part squared. So apply that on both sides. Now we can remove the square root sign from both sides and multiply out what we've got. So this line becomes this line here, and this one becomes this one here. Now do some algebra solving and rearranging, and we'll get 2y is less than or equal to minus 6x plus 8, which gives us y is less than or equal to minus 3x plus 4. So that's the equation of the line here, and we can leave it drawn as a solid line because it's going to be less than or equal to. So the line itself can be included. Now we want it to be y is less than, so we're looking for the things that will fall sort of down towards the left of this line. So we're shading in this side here. Now if you're not sure which side to shade, pick a point on that side and see if it fits. So you can select something like x is minus 4, pop it into here, and see if y was 0 and x is minus 4, would it satisfy this thing? And it does. So we're shading to the left of that diagram. All right, part E is a very heavy algebra question. You might need to pause as we go through to read the bits of algebra that I'm about to pop up. Okay, so we are given this particular bit in complex number stuff. We're told that the real part of it is 0 and z can't be equal to 2. Prove that the locus of points described by z is given by this Cartesian equation. Okay, so you can almost ignore the second part of the question. This is what we're trying to get to. We want to rewrite this in terms of x and y and hope that it comes out to this. Okay, so here we go. First of all, start by saying that z is equal to x plus iy. So that means that z minus I over z minus 2 then looks like this. Now we'll try to rationalize the denominator, and what we're doing here is taking this bit here but multiply it by the conjugate of the denominator. So you'll notice this denominator here is almost the same, but the I part has been turned into a negative. This is to help us to get rid of any I parts on the denominator. So then if we work that through, it turns into this, which is pretty lengthy, but it does help us in the end. So first of all, we can get rid of some of those things at the bottom that cancel each other out. And then we're told that the real part is equal to 0. Now the real part of this is anything that doesn't have an I attached to it. So go along, cross that numerator and take all of the pieces that don't have i's. Now remember that I squared turns into a minus 1, so we do actually include that one here, but it's now a plus because it got times by minus 1. The denominator is all of the bits that were left on the bottom here, and it turns into this. We're told that that real part is equivalent to 0. So now we can go through rearranging. If we brought that denominator up and times by 0, we get 0. So we're just looking at the numerator equal to 0. Now from there, we attempt to rearrange it into this form here. So I'm using completing the square on the x part to make x minus 2 squared minus 1. And then complete the square on the y part. So we get y minus half squared minus a quarter. Those two things will be equivalent because we're trying to turn it into this form that was in the question here. Rearranging that, so taking the minus 1 and the minus quarter, bring it over to the right hand side, and we now have the thing that we were looking for. Okay, question 2, part A, we've got two complex numbers and we need to find z, which is the product of them. Now, we want that in polar form, but you need to notice that we've been given u in rectangular form. So first thing to do is turn it into polar form. So if it's I, then it's straight up on the y-axis, up by 1. So that's a modulus of 1 and an angle around of pi by 2. So that's 1 cis pi by 2. Now, if we times two things together in polar form, then we will multiply the modulus and add the arguments. And that becomes cis 5 pi by 6. For part B, we want to show that this equation has complex roots and find them in terms of k. So we use discriminant to show the types of roots that we have. So the discriminant is b squared minus 4ac. Now if we can show that that's negative, we can show that we will have complex roots. So just popping that in, b here is minus 6k, minus 4 times a, which is 1, and c is 10k squared. So take that through and you end up with minus 4k squared. Now that will always be negative because no matter what k is, it got squared, that turns it into a positive, and then it gets multiplied by minus 4, which will always be a negative. So the discriminant is negative and therefore the roots are complex. Okay, so next is to find the roots in terms of k. So to find roots, we'll use the quadratic formula, and popping in the pieces that we have from our equation, it looks like this. And then working through to simplify. So we can do things like 6k divided by 2. We can pop the 2 inside of this square root and turn it into a 4 to simplify that. Or we can, actually what I did do here was do the square root of 4, bring that out, and then simplify by the 2. And we get 3k plus or minus ki. Remembering that when we square rooted the minus here, it turned into an I. Okay, so for part C, we want to work out the value of k in this. and that value of k is going to be in terms of c and d. We're not going to be able to work it out as an actual number because we don't have any numbers here. When we're told that this thing is completely real, meaning there's no imaginary parts, and c and d are also real constants. Okay, so we're working through with this equation. The first thing to try and sort out an equation with complex numbers is to rationalize the denominator. So we're going to multiply by the conjugate of that denominator, which then gives us this on the right hand side, just multiplying across top and bottom there. So then if we take the I squared, that becomes -1, so we get a plus ck here, and I've brought that over here to put the real terms together. And then we've got the imaginary parts together just here, all over d squared plus c squared, where I squared over here turned into a -1. Now we're told that this is entirely real, which means that the imaginary part is equal to 0. So if we section off just the imaginary part, it's this bit just here. So it's the kd minus c squared over d squared plus c squared. That's equal to 0. Now we can start to rearrange. So we get, if we were to bring the denominator up to the top, it would times by 0. So now just the numerator is equal to 0. And rearranging to get k equals in terms of c and d, then looks like this. So k is c squared over d. Okay, for part D, we're told that some complex number cubed makes -8, and we want to find the value of z to the 4. Now, when working with powers of complex numbers, we want to employ de Moivre's theorem here to make things a little easier. To do that, we must be in polar form. So if we first of all turn z cubed into polar form, if it's at -8 over on the left-hand side of the Argand diagram sitting on the x-axis, then that's going to be 8 cis pi. So it's a length of 8, it's gone 180 degrees around from the positive x-axis. Now that can actually be 8 cis pi plus however many rotations we need there to be of that full circle. So just remembering that that would bring us our first solution, but when we need multiple solutions after that, we just add a whole other circle. So that's what the 2k pi bit is counting up for us. So the first solution here, z1 for this z cubed part, would be that we cube root the 8 and we divide the argument by 3. And that gives us the first solution of what z could be. And that's just using de Moivre's theorem. Now from there, if we were to simplify what we have here, then the cubed root of 8 is 2, and pi by 3 could also have come by adding on another rotation and divide that rotation by 3 too. So our future solutions could also have happened from a full circle added on before we did the divide by 3. So this now is our general solution. So instead of just having the pi by 3, we could also have another rotation that also got divided by 3. Which means that if we're to do to the power of 4, 2 to the power of 4, because remember, look, we're trying to get z to the 4, not just z. So that would have been a 16. And then if we are doing our argument in this thing that got to the power of 4, arguments get multiplied by 4. So each of those things has been multiplied by 4. Now for part E, the theory we're using is pretty simple, but it was hard to recognize it. So the tricky part about this question is how it's been written, and it was hard to notice that it's actually telling us about factor and remainder theorem. So what it's saying is when this thing is divided by this thing, it gives us the same remainder as when the numerator there, which is the same, is divided by that thing. Now what that tells us is if we first set f of x to be this numerator that is the same across all of these things, then if we were to sub in -1 from this bit here, we would get the same answer as if we'd subbed in 4 from this bit here. So that's using the remainder theorem. So now if we do that substitution, so put -1 into this and then put 4 into that, we can set that to be equal to each other. Now working that through, You can pause and read through the algebra if you want. We end up with P is equal to minus 16 over 3. In that working, though, we couldn't work out Q because Q kind of cancelled each other out at this stage here. So we need to use the second bit of information we've been given here. So that tells us if it divides through and gets an answer of 0, then 2 is a factor. So that's the factor theorem. So this bit was using remainder theorem, and now we're going to couple it with factor theorem. So that means if we put 2 into that equation, it's equal to 0. So we work that through. We already know what P is because we worked it out up here. So we substitute that in and we can work through what Q is. So Q is 22 over 3. For question 3, we've got a complex number and we're told its modulus. We're also told the argument sits between 0 and pi by 2. That just means we're looking in the first quadrant and we don't need to think any further than that. So now find the value of k. So modulus means that we take the square root of the real part and the imaginary part from here, and we're going to set that equal to 15. Now working that through means that k squared is equal to 144. So k, if we were just to do this algebraically, k would be plus or minus 144, but we know that we're sitting in that first quadrant, so k must be positive. It needs to be in the top right corner of our argand diagram to make it have this argument. So we're not interested in the negative here, just k equals 12. For B, we've got the area of a triangle. We're told the base of the triangle, we want the height in exact form. So picture this triangle with a base of 2 minus root 3. Now if we were working area of a triangle out, we'd do half the base times the height. So it would look like this. So half base times height is equal to the area we were given here, 3 plus root 3. Now rearrange that to work out h, and we're doing, first of all I times that through by 2, so that gets 6 plus 2 root 3, then divide by 2 minus root 3. Rationalize the denominator, so we can get rid of the surd on the bottom here, and we get this coming out as the answer to that, and that simplifies to 18 plus 10 root 3. For part C, we're told we have a solution to this equation here. We want to find the other solutions. We know there will be 2 more because this is a cubic. So first of all, putting that solution in to this equation and simplifying what we get gets us this far. Now if we take out the real and imaginary sections of that, so all of the real parts of this come to this, they will be equal to 0 because it's equal to 0 on the right hand side here, so the real part on the right hand side is also 0. Now the imaginary part, all of the imaginary bits of this left hand side will be equal to 0 because the imaginary part of the right hand side is 0. Now taking that through to solve gets us the values of a is minus 5 and b is 11. So we're solving simultaneous equations here. You can pop them into your calculator to get those values. The second solution is 1 minus 2i. Now that is straight away from knowing it's the complex conjugate of 1 plus 2i. So we've got the values of a and b, and we've got the second solution. Now we just need the third one. So putting these into factor form, we would have 3 factors. And you can see there's one factor here, which is x minus, oh, I've missed a bracket, just a sec, I'm just going to fix that up. Okay, back to where we were. This is one factor here, which is x minus the first solution, the one that we were given in the question. X minus the second solution makes our third factor here, 1 minus 2i. And x minus the third solution that we're trying to work out would give us a third bracket. So this third piece here is the third solution that we're looking for. So if we multiply out that bracket, we get this answer just here. Now comparing the constants, just look at the things that make a constant come out of this is the complex number here times that complex number there times c. Now those two multiplied together make 5. You can do that on the calculator. 5 times c is got to be equal to minus 15 on the right here, so therefore c must be 3. which means that in this bracket, the c is a minus 3. So x minus 3 is a root, and our third solution is x equals 3. Okay, part D is just a bit of hard graft of algebra work. So we're solving this equation. To sort out the fact that there's a square root on this side, we need to square both sides. Now remember, we're not squaring the individual terms on the left-hand side, we need to square the whole thing. So that's a double bracket approach. So multiplying that out, we get to this line here. Now the k squared x cancels out, and if I rearrange the 16 over to the other side, so because we're trying to isolate the x here, then we can divide through by the minus 8k and square both sides. Okay, part E, we've got two complex numbers, u and v. First write u over v in a plus bi form, and then find the angle AOB. So we've got u over v, that's the easy part. You can do that on the calculator. So we would go to minus 4 plus 2i and divide it by 3 plus I, and we get minus 1 plus I. Now plot this onto a diagram, and we have u making the A part and v making the B part, and we're trying to find the angle AOB, so the bit between. Now to work out that angle, we'll do the argument up to A minus the argument up to B, and that will leave us with the bit in between. So AOB will be the argument of u minus the argument of v. Now if you think back to de Moivre's theorem, if we're subtracting the two, we can divide like this. So the argument, when you're subtracting two arguments, it's the same as if you'd done the argument of the division of the two things. So this would be the same as the argument of minus 1 plus I, so u over v. Now that sits just here on the diagram. Thinking about where that is on our argand diagram, it's at minus 1 plus 1, so it looks like this, which makes it an isosceles triangle with the quarter there of a 1, 1. So that means that the argument from the positive direction will be 3/4 of pi. There you have it. Hopefully that was useful to you to get a bit more practice in before your externals. And if you found it handy, please like and subscribe, share it with friends, drop me a comment, tell me how awesome you're going to do on these exams coming up. All right, see ya.